live stream and cat stream and book stream with you, where we've been covering topics from this book called Einstein's Cosmos by Michio Kaku. This is how Albert Einstein's vision transformed our understanding of space and time. And we have actually covered quite a few topics from this already. We spent some time talking about special relativity and also Einstein's life and his life around then, his struggles in the beginning of his career, sort of earlier in his school years, and even through graduate school type of years. Some of the struggles that he had, we talked about it, and how 1905 was really a very amazing year for him and for physics in general. Hi, Valentina. How are you? So I wanted to show you the kitty cats as well. See, Fuji's over there. He is minding his business. They just had their dinner. And actually, Baji and Suji have started a play fight and chased each other to go upstairs. So even though we usually start this live with Baji and Suji, or at least one of them together here. Right now, all I have for you is Einstein, which I think is more than enough for the most part. And I love Fuji. Oh, thank you, my baby. Yes, so Fuji is my extremely special child. So I try to show him less because I don't really like sharing him. But with Baji and Suji, most people have a lot of fun with them and their various expressions and things that they have to offer to this world. But let's see if Baji and Suji will come down during this live. Okay, I'm trying to click on the live as well on my channel, and currently it doesn't look like I can click on it. Maybe I am imagining this. So hopefully we are live, and hopefully you are real and I'm real and we're actually live. Reality, of course, can be relative. The other cats are upstairs where the Wi-Fi does not work. So they will come down momentarily, I'm sure. They always do. They can't really stay upstairs for that long because they miss their mother. That's me. So, Suji Baji. Let's see if I call them if they come down. It'll be a big test. Suji Baji. Baji Suji. Suji. Suji Suji. Can you break it down in front of my face? Break what down? So anyways, I think we'll continue with our topic for today because I promised that we would cover grand unified theory on the live stream today, and the physics Fridays are more about the physics topics than anything else, although we are generally accompanied by the kitty cats. So let me just recap for you what we've been talking about. So we know that Einstein had some initial struggles in his life. And in fact, he found the education system in Germany to be quite difficult and challenging and rigid for someone like him who had plenty of imagination and wanted to break free and have more freedom to kind of think and do things in his own way. But then he had a lot more luck in Switzerland, in the Swiss system, and that's where he continued some of his higher education. But even then, he was actually having trouble finding an academic position or a graduate student type of position or assistantship, and we kind of saw some of those struggles and whatnot. And he, of course, got the job in the patent office. And it was really at this time that he also kept up with his physics pursuits, and he even made a study group, and that kind of helped him a lot to collaborate and still keep up with all of the developments in physics at that time, all of the sort of conflicting work and conflicting type of evidence and physics that was kind of coming out at that time. For example, the conflicts with classical mechanics and what it was saying versus what he was finding with Maxwell's equations, and sort of this not being able to understand, light and the pun intended, light that was shed on E and M by Maxwell's equations and things like that. So he himself took a stab at that. And remember, of course, at that time in the early 1900s or late 1800s, they were thinking that there is something like ether, and this must be the one that carries light to us, because light was an electromagnetic wave, and people were just not sure how it was reaching us from faraway places like the stars and things like that. So this is kind of when he worked on special relativity, when he came up with his new updated theory of light and explained things in his way with special relativity, which also became sort of the updated theory, which helps to set the stage for E&M, electricity and magnetism, and also to understand how light works. And not just that, in the year 1905, he also worked on, a number of interesting things, really. So special relativity, the whole, the space time being relative, that was something he worked on. Energy and mass equivalence is something he worked on. He also worked on, of course, the photoelectric effect, and also on Brownian motion. So this was all happening in 1905. And it was a very, very successful and path-breaking year in physics. And then he went on also to work on general relativity. So remember how he was very impatient with himself, with the progress he made in special relativity, and how it was only working for inertial frames. And he wanted to extend that to, of course, general relativity, which is a more updated theory of relativity and includes non-inertial frames. And it is also the updated theory for gravitation. So I'm just kind of bringing you up to speed with the things that we have already covered. I know that these are the things that we have already covered. I'm recapitulating for you what we've covered so we can get into the grand unified theory. Make your tea. Yeah, maybe that might be a good idea. I was gonna jump into the live stream, but maybe I should give it a few minutes for people to join, and things like that. I could do that. Yes, indeed. The Friday physics live stream goes pretty long. I will warn you. I might even break it into a couple parts here, and things like that. But it goes well into the night, especially if more people join and people are showing interest in the physics topics. Then generally it kind of keeps going for a while and into the night. So get yourselves comfortable. Get yourselves in a good position under a blanket or something like that if you need, and get some popcorn, get some food. And hi, guest not found. Hello, I'm comfortable. Okay, good. Desi Food by English Cook. How are you? Desi Food by English Cook. That's a very nice name. And thank you for the flower emojis. Guest not found said hi, and I'm back. Very nice. Okay, guys, thank you so much for joining. I don't know if my usual set of friends of the channel are getting that we're live or not. Maybe I'll share it again. And then also, as Valentina suggested, maybe I'll make my tea so that we can give it a few more minutes for this live stream to kind of get going. And I'll put the phone over here so you can see Fuji as well. And Baji and Suji are still upstairs. They're doing their thing upstairs. Hi, Fuji. You can give them a little company. And then we'll get started, okay? Good job, Fuji. Good job. I have to clean my kettle first. Fuji! Yes, box kitty. Yes, this is his box that his food came in. His food came in this box, and he has since claimed the box, and he does not move from it. Like when he's comfortable in the box, he stays in the box. And the box says thank you. So thank you for joining, everybody. Here's Flowey. And he stays put in this box because it says thank you. And it's his box, right? Baby Shona, to tumi to Shona. Shona to tumi. Bishon bhalo ekta chele. Okay, I will not disturb you, Fuji. I will not disturb you. Evil Eye removed from Fuji because he's too cute. It is true that my physics crowd is generally more late, like they join like super late at night, like 11 p.m. or midnight or even 1 and 2 in the morning here in Boston. So it could be that I've gone live a little too early, but that's fine because I'm happy to go live again. Maybe take a break in between and we can go live again in a little bit. Today's a rainy day in Boston. Like it just started raining. Actually, like, aw, the cat is inside the box. Yeah, my package is moving. Can Fuji be my friend? Fuji, do a weird meow. Guest not found is requesting a meow from Fuji. Can Fuji be my friend? He is very selective. He's very, he's got a whole personality of being quite picky. Fuji, Baba, छोटू Baba. He's the one who gets mad at me for kissing him too much. He gets very mad at me sometimes, but only momentarily. He actually likes it. When I'm sleeping in the morning, he gets very worried, thinking that he's like, why are you still sleeping? He doesn't realize that humans need more sleep, and he climbs all over me, and he's always like checking on me to make sure that I'm okay. He's such a sweet too. Choto Puchi. Fuji be. Yes, Fuji can certainly be your friend. He's a baby. He's a baba. He's a baba. He's a baba. Okay, so I filled it up with water. Now I will start the kettle so that, see, I've got the water in the kettle. Now I'm going to start this process of actually boiling the water. If you're joining, thank you. Keep on joining. We're going to be studying physics for sure, and we're going to get cozy. And so please do join and be here. Okay, Fuji Baba, I have started the kettle. I've plugged it in. Now it's started. Oh, look! Valentina, you said that yours turns blue, right? Mine also turns blue. Screenshot time. Tea time, yes. Hi, Big Changa, how are you? Big Changa, thank you so much. Big Changa said nice cat. Valentina said tea time, screenshot time, yes. So yeah, this is the kettle I got off of Amazon. This is not like an ad or anything, but as I was making the tea, Valentina here said that she has the same one. Hi, Baji Baba. Oh, hi, Neeraj. Neeraj Chaturvedi is saying, it's a pleasure meeting you, myself, Neeraj. Yes, I got mine from Peru. Hi. Hi, Baji. Oh, Baji did a meow. Baji did a meow. Baji, you're late to your own live stream. You know, you are the main host of this channel, and Mama's been doing the physics readings and studies on Fridays, along with your face for the branding. But, you know, he was busy upstairs. He was very busy upstairs chasing his sister and not really being able to successfully catch up to her because she's too fast. Come, Baji. Yes, Baji can read. You have such a nice and genuine heart. It's really rare to find. Thank you, Neeraj. That's very nice of you to say. Can Baji read? Yes, he can. And Fuji here has a whole physics PhD. He even wrote my thesis. So, absolutely. Big kiss for Fuji. Evil eye remove. Evil eye remove from my baby. Oh my gosh. Hi, Baji. Hi. Hi. Hello. I guess I'll sit down on the floor. Baji. Hi, Baj beautiful. Do you have a Roomba? Sort of. I have it. I have the Roborock. I have the Roborock vacuum, not a Roomba. It's kind of cheaper than the Roomba. Hi. Did you hear that? Baji. Baji did the meow. So Baji actually replies, when I said hi, he said meow hi. He said meow hi. Baji. Oh, Baji. Baji. Oh, ho, ho, ho. Oh, ho, 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 ho. Baji wants love, love. Hello, do you remember me? Yes, Rubiela, I do remember you. Baji did a meow and asking for more love, please. Oh, guess not found. Hi. Rubiela says, do you remember me? Indeed, I do. Thank you, Desi Food by Chicken, or sorry, Desi Food by English Cook. I don't know why I said chicken. Rubiela says, I'm the son. Oh, that's right. You're the son of Rubiela. Got it. Hi. 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 Hi, hi. Hi, 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 hi. Hi, 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 hi. Oh, this Baji Shona. Oh, this Baji Shona. Oh, ho, 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 ho. ওলে বাবা কি সুন্দর ছেলে একটা কত সুন্দর কপাল he has such a nice cute forehead he has a nice cute forehead that's right I remember you Rubiela's son thank you for joining we will be doing some physics topics today Baji wants my fish. That's possible. Although Baji's not much of a hunter, to be honest, he's not really very vicious. He's more sort of docile and domesticated. He kind of lets his food come to him, you know, in a platter. Hi, Baji. He kind of just lets things come to him. He believes in the law of attraction. Rubiela says, TK, thank you. My pet, I'm in love with your cats. Thank you. Me too. We have the same state. We have the same. Woo hoo 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 hoo. Baji Baji. Shona Baji. Shona Baji. Shona Baji. Baji. Choto Baji. So he has, so actually I think Baji is kind of hoping for something. He's a little bit hoping for some kinda like treat-dos or something. Although he did have his dinner. Come, Baji. Come. See, he wants love. I think right now he's not really hungry, but he came down after he attacked his sister to see if he could get some extra loves or not. um, Valentina says the cat family. Yes, indeed. And look, my water's boiling over there. It's nice to look at it, kind of. It's boiling, boiling. And here's Baji. Oh, baby. He's all cuddled up and he's purring. 1, 2, 3. Hello. Hi, Valentina. She said they have cute names. And Rubiela, Prednisone. That's possible. Prednisone. I'm not sure what that means, but it sounds like a pretty word. Okay, Baji. Now that Baji's on my lap, Fuji has his eyes closed over there. Now that Baji's on my lap, I'm not sure I can get up to finish making my tea because I have a cat on my lap now. It's a done deal. It's a done deal. We can't move now. Ole Baba. How many points without breathing? I'm not sure what that means. Indeed, I'm not sure what that means. Okay, so I think we'll get started with the reading while Baji's on my lap so that we can make a little bit of progress. And then once he's off my lap, I can get up and finish making my tea. But I do want to make some progress with the topic that we said we would cover today, and it is a Physics Friday. So please hang tight. If you feel like it's a little confusing, just stay with us. I do a lot of explanation on the side, and I also provide a lot of context with what we are reading and what we are covering from the book, from my own experiences as a physicist and getting training in physics. So, how many points can you get without breathing? I'm not sure what this means. What are we doing? So we are going to be reading from this book, Einstein's Cosmos, and we're going to be covering this next chapter that we're on, chapter 7. And I'm also going to be providing context along the way and doing a discussion of physics from my own background. So let me get started and you'll kind of get the hang of it as we keep going. So I was starting this live stream. Oh, hi, Rubiela. How many pages are there? Well, there's lots of pages, but we're not going to cover the whole book today. We'll just cover a part of it. So hang tight. You almost died? Oh, gosh. Well, that's too bad. Oh. Okay, Baji, shall I get up and go get my tea first or not? That's too bad. That's too bad, Baji says. I think I'm going to have to sit here and read like this. So let me get started. In 1905, almost as soon as Einstein worked out the special theory of relativity, he began to lose interest in it because he set his sights on bigger game, general relativity. So remember, we covered what we had talked about with special relativity was in 1905, he had a very big year. He came up with the theory of relativity. He came up with how space-time is relative. He came up with mass-energy equivalence. He also worked on the photoelectric effect, and he also worked on Brownian motion. And later on, he actually got the Nobel Prize for the photoelectric effect. But then, remember, he was not happy with that or content with that in the sense that he moved on to keep on working to generalize special theory of relativity and cover more scenarios, not just be able to explain inertial frames of reference, but also non-inertial frames of reference where there is acceleration, including, of course, gravitation, because in a gravitating system, of course, there's acceleration. The moon is accelerating towards the earth is accelerating around the sun. So he realized that if you only are limited to inertial frames of reference, which means no acceleration, then that is not most of the scenarios that we that we think you that we encounter in real life, right? Real life includes a lot of acceleration, and it includes scenarios with acceleration. So what I'm trying to say is he was very aware of his own limitation in special relativity, and he generalized it to general relativity, which is a whole thing. It was a lot of work to come to general relativity, and it includes very complicated math, or at least mathematics that a lot of people find to be complex. And he did too, but he did not let that limit him. He kept on going so that he can cover and properly come up with this new updated theory of gravitation. And in fact, sort of evidences of that. This is relaxing. Oh, good. Yeah, take a nap if you need to. With this live going, don't leave the live. Don't leave us, but get settled and relax. So he kind of had ambitions even when he was doing a lot. And even when he got bigger results, he kind of kept going because he wanted a more complete picture, a more fuller picture for physics and for explaining this universe. This universe, of course, contains inertial frames of reference. It's good to start there because you can at least show your results and show your theory and get it proved out for an inertial frame of reference. For those special cases. But of course, it would be good if you could generalize it to also include acceleration. And with this, he came up with a new updated theory of gravitation, because remember, classical mechanics given to us by Newton back in the 1800s had really actually given us a theory of gravitation, and that's what was still working for us. And even today, it kind of works for us for the most part. But when you want a more complete theory for gravitation, when you want something that works in a more updated manner, is true, and even works at a cosmic scale, and takes into account the space-time or the relative nature of space-time and all of that, then you get the more updated theory, which is the general theory of relativity. Now, we did a lot of, this is perfect. Oh, good. We did a lot of talking and conversations about this last time during our Physics Friday live last week. And we basically finished the topic of general relativity, or at least we covered it comprehensively. And we even started to look at some of the evidences. So, he came up with a theory, but that's not the end all be all, because it still has to be shown in real life with physical evidence, and evidence is coming from astronomy. And actually what happened was he also, basically him and Hubble ran into each other through all of this, and Hubble actually showed us, Hubble is an astronomer, he showed us with actual physical astronomical evidence that, all these things about there being more galaxies, our galaxy, the Milky Way, is not the only galaxy out there, and sort of the predictions that came out of Einstein's theory of general relativity. He actually came up with some of the evidence of that. So, because Einstein came up with the theory of general relativity, which has certain predictions, but if those predictions are not proved out with real life experimental evidence with astronomy or astrophysics, then it's actually not, that's not really how it works. We want sciences. And in fact, even in the last decade, even very recently in the last few years, still more evidence and still more sort of confirmations of his theory is still coming in, actually, as we gain more and more capabilities to do these experiments and to have better observation equipment and astronomy updates and upgrades to be able to actually prove out his theories and his predictions. Because if he predicted something that was hard for us to observe and we didn't have the ability to, then we wouldn't be able to, but now we can. Okay, so that's sort of the status of where we are in the book at this time, is where we left off. But then, and we saw that even when during his lifetime, there was significant progress in getting evidence to confirm his theory. But he was not just content with that. He actually wanted to extend it further. And that's where the grand unified theory comes into play. And this is what we'll read about right now. Okay, so, hi Baji, are you comfortable? He's comfortable. Thank you for joining. Thank you for being here. Please share the live if you can. We'll keep going. In 1905, almost as soon as Einstein worked out the special theory of relativity, he began to lose interest in it because he set his sights on bigger game, general relativity. In 1915, the pattern repeated itself. So now we're going to get into 1915 timeline. This is still over 100 years ago, of course, but you will see how very interesting things happen at that time. And really another motivation for covering what I call the 20th century physics, because this is the 20th century that we're talking about in the 1900s, is that the 20th century physics really laid a lot of foundation for what the big mysteries of today are. So I've mentioned in my previous live streams that today in astronomy, or cosmology, astrophysics, whatever you want to call the field, today the big questions that are still outstanding, as in they have not been answered, the biggest mysteries of the universe today are, number one, what is dark energy? Number two, what is dark matter? And number three, there are still questions about the origin of certain elements. So, because ordinary matter, the elements that we know from the periodic table, make up all of the matter that we know, it would be good to understand exactly how they're made and what processes. And although we know to a large extent a lot about this, there are certain elements that we still don't know fully how they're made. And that's why I mentioned that in the top three questions. At least for me, and I think at least for a lot of people, those are the top three questions. But the first two that I mentioned, the nature of what is dark energy and the nature of dark matter, these two things especially form some extremely big unanswered questions or mysteries of the universe, which would be very pertinent for all of us to kind of pursue, or at least be able to see the results of what is happening with that. But we cannot really understand these without first getting up to date with the 20th century physics. And I think what I'm doing here, this science communication, is sort of what we owe to the public, actually, because it is your tax paying dollars that actually fund these science projects. So I think you have a right to know actually what goes on and what work is done, and to understand that you need this background, okay? So we'll keep reading. As soon as he finished formulating his theory of gravity, he began to shift his focus to an even more ambitious project, the unified field theory, which would unify his theory of gravity with Maxwell's theory of electromagnetism. It was supposed to be his masterpiece, as well as the summation of science's 2,000-year investigation into the nature of gravity and light. It would give him the ability to read the mind of God. Einstein was not the first to suggest a relationship between electromagnetism and gravity. Michael Faraday, working at the Royal Institution in London in the 19th century, performed some of the first experiments to probe the relationship between these two pervasive forces. He would, for example, drop magnets from the London Bridge and see if their rate of descent differed from that of ordinary rocks. If magnetism interacted with gravity, perhaps the magnetic field might act as a drag on gravity, making the magnets fall at a different rate. He would also drop pieces of metal from the top of a lecture room to a cushion on the floor, trying to see if the descent could induce Turn the page. Could induce an electric current in the metal. All his experiments produced negative results. However, he noted, they do not shake my strong feeling of the existence of a relation between gravity and electricity, though they give no proof that such a relation exists. So these people, Michael Faraday, remember, had a pivotal role in updating electric and magnetism, electromagnetism, the theories, because he actually discovered that changing electric and magnetic fields can kind of interchange into each other. He's a very experimental kind of guy. He gave us a lot of, oh, there's Suji. He gave us a lot of very important experimental insights that actually showed us certain things. And remember that people like Faraday, Michael Faraday in Britain, Maxwell, these were the people whose work greatly affected and impacted Einstein in a good way, because he was able to draw an even more foundational insight from their already existing work. So we must thank Faraday and we must thank Maxwell and others for the work that they did prior to Einstein, and to lay the foundation of these new understanding of electromagnetism that we came up with. The fact that electricity and magnetism, the changing electric fields can turn into magnetic fields, changing magnetic fields can turn into electric fields, this sort of thing. And also the fact that the speed of light is a constant, these come from the work of such people. So we will be grateful for their work. And they continued to keep on contributing with these various experiments they did, even though they might sound sort of basic now. But remember, back then, when they were still trying things, and experiment is really the way to go. Even if the experiment has certain limitations, you still learn that during the experiment. Your results from an experiment could literally be, well, this was limited because of this other effect, so we couldn't really conclude that. But even that is a result. Actually, not getting the result you wanted or predicted is still a result in experiment. It's a very important result, because theories by themselves is not enough. They don't give you that confirmation, that actual reality that you would need in experimental science, which physics is a part of. So that's why it's so important to have people like Faraday and to be inspired and understand what people like Faraday were trying to do, because this is very basic to the mechanism of doing physics. Okay, so with that being mentioned, he had a strong feeling that there was a relationship between gravity and electricity, but he wasn't able to find the proof of it. He was kind of struggling to find the proof of it, but he tried. Furthermore, Riemann, who founded the theory of curved space in any dimension, believed strongly that both gravity and electromagnetism could be reduced to purely geometric arguments. Unfortunately, he did not have any physical picture or field equations, so his ideas went nowhere. So basically, Riemann is somebody who... do we need to answer questions after this? Maybe. There is a quiz. Yes. So pay attention. Riemann, remember, is a mathematician. So he came up with mathematics to kind of show the theory of curved space in any dimension. If you tack on more dimensions, maybe there is an explanation. But most importantly, for physicists, we need a physical explanation of something. It has to be a physical science. Because remember, dark matter, dark energy, why I'm saying that these are still unanswered questions is because we don't know the physical reality of these yet fully. But remember how black holes was an example of something that was also sort of a mystery, or something that people thought could not exist, would not exist, was too fantastic or something. But remember, actually, black holes are a physical reality. We found physical evidence of them. They are actually a scientifically proven physical reality. So that is actual science, and black holes are real. The thing that people thought was so fantastic actually is real. And, when we covered black holes last time, we know that they're real. So they were called dark stars. So out of the three dark things, dark energy, dark matter, and dark stars, black hole being the dark stars are actually real. We have made a lot of progress understanding them. But dark matter and dark energy are still not real in the sense that there is not a physical, direct evidence, okay? Of what they mean is what I mean. We have evidence that we need something, that we needed a placeholder, and we gave the names dark energy and dark matter to that placeholder, but we still don't have the physical evidence of this and or the physical science of them. And that's the important thing to know and understand. So, this whole thing with the grand unified theory, it's important to keep in mind like what we're trying to do, why these people wanted to unify these theories. They had a perhaps a strong instinct about something. So sometimes in theorizing something, a scientist might be sort of following a strong instinct that they have about something, and it's still a hypothesis or a theory. It's not necessarily something that they have been able to prove out with actual physical evidence. So that's important to keep in mind. You know, not everything is sort of real yet, but that does not make them, it's still worth pursuing. And especially if you are a more established scientist, then you could actually pursue whatever you wanted and it would be fine. It would probably be funded. It would be supported by somebody just because they have the faith in you, you know? So it's kind of nice to get there in your scientific career where you can just kind of pursue things that you want. And if people are willing to fund it, given that there's a lot of potential in that direction, then there you have it. You get to kind of pursue something that you want to, just because you want to, not because of any real practical reason yet, or maybe not a practical reason that has shown itself yet. So that's really what the pure science career is about. Okay, not everything has to have a practical application right away for it to be pursued in the pure sciences. Valentina says, I want to learn about the human body. Cool. Einstein once summarized his attitude toward unification by comparing marble and wood. Marble, thought Einstein, described the beautiful world of geometry in which surfaces warped smoothly and continuously. The universe of stars and galaxies played out their cosmic game on the beautiful marble of space-time. Wood, on the other hand, represented the chaotic world of matter, with its jungle of subatomic particles, its nonsensical rules for the quantum. This wood, like gnarled vines, grows in unpredictable and random ways. New particles being discovered in the atom made the theory of matter quite ugly. Einstein saw the defect in his equations. The fatal flaw was that wood determined the structure of the marble. The amount of bending of space-time was determined by the amount of wood at any point. So at this point, basically what is happening is that he's worked on Baji is Einstein. Yeah, and there is Suji. She has joined us too now. Baji is understanding Einstein. And there is Mama. There is my Suji Mama. Basically, at this point, remember, of course, classical mechanics is the thing already. It has been a thing for 200 years because Newton worked on that in the 1800s. Actually, even earlier, maybe. So, by the end of the 1800s, this classical mechanics was already very established. But then Einstein came up with special relativity and general relativity, as well as there were... Oh, my dishwasher just finished. Hi, dishwasher. General relativity, and there's also progress in E&M. But then, in parallel with that, there was also progress in quantum mechanics. So remember, we kind of mentioned Max Planck in the earlier episodes. Okay, dishwasher, where he had made leaps and bounds into the quantum mechanics theories, and that also plays a role in what people are thinking now, what the scientists are thinking now. So as Einstein is coming to know about more quantum mechanics, he's probably kind of pondering about that as well. Actually, let me go turn it off. Baji, you have to move for a second. Let me go turn that off and make my tea and then bring that back here, so that we are not disturbed by this noise. Yeah, just gotta turn this off. Hi! Hello, I'll put you guys down over here so you can still see Baji and Suji, and I'll make my tea. And you guys can keep on sending your typing your chat messages. Whoops. I think it stopped raining. Actually, I need a mug from the dishwasher, so I'm glad it finished. Oh my god. Oh, hello. Lots of steam. Hello. Good afternoon. Good evening. Good night. Thank you for joining. Let me actually share the live again as well, because I'm not sure that people know about it yet. Thank you for being here, everybody. It's my, whoops, there it is. It's on my iPad now. I love you, Suji. Aww. Valentina said Baji's Einstein. Cuddle Juice said, how old are you? I love you, Suji. And then Cuddle Juice asked, are you Arab? I am not that I know anyways. Yeah. Just a question somebody asked. That's all. Whatever. We are live. Join us. Yay! I'm just sharing the live again on my community tab. We're live. Join us. Yay! You're kind of glitching. Am I glitching? Oh, sorry. Is it all right now? The topic today is the grand unified theory that Einstein was working on. Okay? And more generally, the topic is physics. I don't know what that is. Great. Now you will learn. You can know what it is if you stay in the live. Okay, my darlings. Good job. Good job. Good job. Can everyone please share the live too, or like the live, and well, share it if you feel like sharing it with somebody or something. Will there be a quiz after? Yes. It'll be a friendly quiz. Wow. I mean, generally we just have a, fun chat. Nothing too Nothing too stressful for most people. It's just a learning thing. You know? Nothing to worry about. Oh, Fuji looked up because he thought I'm taking out his food. I'm just taking out the scissors so I can cut open my tea, my friends. Oh boy. Oh, okay. All right, almost done with the tea making here. All right. The tea is good. It's a spicy chai. Okay, so we will continue our discussion. Hi, Chloe. How are you? Here's Baji. We're covering physics. I have learning disabilities. Hi. Hi, No Wonky. How are you, my darling? I have learning abilities. Good. Very nice. Chloe says, I love Suji. Thank you. Here is Suji and Baji. So basically, you know, the nice thing about these live streams is if anything is less accessible, you can always listen to it again by going back. And once the live stream is available on the channel as an upload, you can always, play it again. I love seeing the kitties. Thank you. No Wonky. It's been a while. We've been doing the live streams with kitty cats and physics topics, so it's been nice to see everybody. I love your videos. Oh, thank you, Chloe. Thank you so very much. Here is Suji. Aw. Thank you for the emojis. Thank you, thank you. Can we start with the lesson already? Did you make your tea? I did. Yes, I'm taking a few sips of it. Thank you so much for joining. I'm from Alpha Centauri. Very nice. All right, so we will get started, as in we will continue. So Einstein was having some issues with finding out more truths about the atom. The fact that the atom was not fundamental, as in it was created of more fundamental particles, and all these more details were kind of coming out with the advent of quantum mechanics. This was actually kind of creating complications in his mind where he was having trouble in sort of unifying everything together. So that's what we're reading about today. And as we read more about sort of his struggles, it will hopefully illuminate to you as well what these topics are, and you can get caught up with them. Proxima B. Okay, cool. So, thus to Einstein, his strategy was clear to create a theory of pure marble to eliminate the wood by reformulating it solely in terms of marble. If the wood itself could be shown to be made of marble, then he would have a theory that was purely geometric. For example, a point particle is infinitely tiny, having no extension in space. In field theory, excuse me, sorry, I have to, okay, 1 second. Okay. In field theory, a point particle is represented by a singularity, a point where the field strength goes to infinity. Einstein wanted to replace the singularity with a smooth deformation of space and time. Imagine, for example, a kink or a knot in a rope. From a distance, the kink may look like a particle, but close up, the kink or knot is nothing but a wrinkle in the rope. Similarly, Einstein wanted to create a theory that was purely geometric and had no singularities whatsoever. Subatomic particles like the electron would emerge as kinks or some kind of small wrinkle on the surface of space time. The fundamental problem, however, was that he lacked a concrete symmetry and principle that could unify electromagnetism and gravity. So he's basically kind of grappling with the fact that matter has all these complications. The atom is, mostly empty. It's made up of more. This is perfect. Okay, good, Chloe. Thank you. It's made up of more fundamental subatomic particles like electrons and protons and neutrons. There is also the theory of electromagnetism. Of course, electrons would be a part of that, right? Electric fields, right? Electrons. But he's kind of not able to. Hi, Rosie. Hi, here's Baji. How are you? You're kind of glitching. Am I still glitching? Sorry about that. I don't know if I can do anything about it. Sorry. But basically, he is trying to unify together these different. I'm good. Okay, good. These different sort of parts of physics. Some of them are to do with matter and how matter is made up of atoms and atoms has electrons. It's not the glitches. It's your microphone. Okay. I'll try to hold it a little bit farther away from me because it might be getting bumped, like just the phone and stuff, so I think it's getting bumped. Sorry about that. Yeah. So anyways, he's trying to unify together these things. With special relativity, he had the picture that guided him constantly, running next to a light beam. This picture revealed the fundamental contradiction between Newtonian mechanics and Maxwell's fields. From this, he was able to extract a principle, the constancy of the speed of light. Last, he was able to formulate the symmetry that unified space and time, the Lorentz transformations. Similarly, with general relativity, he had a picture that gravity was caused by the warping of space and time. This picture exposed the fundamental contradiction between Newton's gravity, where gravity travels instantaneously, and relativity, where nothing can go faster than light. From this picture, he extracted a principle, the equivalence principle, that accelerating and gravitating frames obeyed the same laws of physics. Last, he was able to formulate the generalized symmetry that described accelerations and gravity, which was general covariance. The problem facing Einstein now was truly daunting because he was working at least 50 years ahead of his time. In the 1920s, when he began working on the unified field theory, the only established forces were the gravitational and electromagnetic forces. The nucleus of the atom had only been discovered in 1911 by Ernest Rutherford, and the force that held it together was still shrouded in mystery. So, there's the strong force that we know about now, which rules the subatomic particles, but this was not yet known at that time. So, what he's trying to do in short is difficult because he doesn't have the full picture of all the forces and all the different things that are at play. But without an understanding of the nuclear forces, Einstein lacked a crucial part of the puzzle. Furthermore, no experiment or observation exposed a contradiction between gravity and electromagnetism that would be the hook Einstein could grab onto. So he's just kind of reaching out for things that is not accessible yet to him because that knowledge is not accessible yet to him. Hermann Weyl, a mathematician who was inspired by Einstein's search for a unified field theory, made the first serious attempt in 1918. At first, Einstein was very impressed. It is a masterful symphony, he wrote. Weyl expanded Einstein's old theory of gravity by adding the Maxwell field directly into the equations. Then he demanded that the equations be covariant under even more symmetries than Einstein's original theory, including scale transformations, that is, transformations that expand or contract all distances. However, Einstein soon found some strange anomalies in the theory. For example, if you traveled in a circle and came back to your original point, you would find that you were shorter but had the same shape. In other words, lengths were not preserved. In Einstein's theory, lengths could also change, but they remained the same if you came back to where you started. Time would also be shifted in a closed path, but this would violate our understanding of the physical world. For example, it meant that if vibrating atoms were moved around a complete circle, they would be vibrating at a different frequency when they came back. Although Weyl's theory seemed ingenious, it had to be abandoned because it did not fit the data. In hindsight, we can see that the Weyl theory had too much symmetry. Scale invariance is apparently a symmetry that nature does not use to describe our visible universe. So if you had too much symmetry in your theory, it might not work, is something that is kind of revealed with this finding. In 1923, Arthur Eddington also caught the bug. Inspired by Weyl's work, Eddington and many others after him tried his hand at a unified field theory. Like Einstein, he created a theory based on the Ricci curvature, but the concept of distance did not appear in the equations. In other words, it was impossible to define meters or seconds in his theory. The theory was pre-geometrical. Only in the last step would distance finally appear as a consequence of his equations. Electromagnetism was supposed to emerge as a piece of the Ricci curvature. So they're trying to kind of make E&M come out of the Ricci curvature of this, from the space-time work, but it was not. It was not coming out of it. They were not being able to unify his general relativity with that. So the physicist Wolfgang, the physicist Wolfgang Pauli did not like this theory at all, stating that it had no significance for physics. Einstein also handed, thinking it had no physical content. So some of the things are coming out of mathematics, and some of the physicists like Wolfgang and even Einstein is saying, well, this is a math thing that falls out of this symmetry or whatever, but it does not have a physical content. Like what I was saying earlier, like it's one thing to give something a placeholder and to say that the equations require a placeholder like dark energy or dark matter, but it's another thing to kind of say and prove that it has a physical meaning, if you will. Like having physical content is a different matter. Give me 1 second, actually. I had to check something that was working or not. Sorry about that. We're back. If the picture kind of glitched, it's because I had to check a different app on my phone. Sorry about that. Okay, we're back. No worries. So this lack of physical content is something that was bothering him. Like some theory, some symmetry, some mathematics is not enough. You have to kind of find the physical meaning of it. But what really rocked Einstein to the core was a paper that he saw in 1921, written by an obscure mathematician, Theodor Kaluza, from the University of Königsberg. Kaluza suggested that Einstein, who had pioneered the concept of the fourth dimension, add yet another dimension to his equations. So Kaluza is saying that you should add another dimension to your equations. Kaluza began by reformulating Einstein's own general relativity in 5 dimensions: 4 dimensions of space and one dimension of time. This takes no work at all, since Einstein's equations could easily be formulated in any dimension. Then, in a few lines, Kaluza showed that if the fifth dimension is separated from the other four, Einstein's equations merged along with Maxwell's equations. In other words, Maxwell's equations, the horrible set of 8 partial differential equations memorized by every engineer and physicist, can be reduced to waves traveling on the fifth dimension. To put it another way, Maxwell's theory was already hidden inside Einstein's theory if relativity were extended to 5 dimensions. Einstein was surprised by the sheer audacity and beauty of Kaluza's work. He wrote Kaluza, "The idea of achieving unification by means of a 5-dimensional cylinder world never dawned on me. At first glance, I liked your idea enormously." A few weeks later, after studying the theory, he wrote, "The formal unity of your theory is startling." In 1926, the mathematician Oscar Klein generalized Kaluza's work and speculated that the fifth dimension was unobservable because it was small and possibly linked to the quantum theory. That's right. That's right. Kaluza and Klein were thus proposing an entirely different approach to unification. To them, electromagnetism was nothing but vibrations rippling along the surface of a small fifth dimension. For example, if we think of fish living in a shallow pond, swimming just below the lily pads, the fish might conclude that their universe was two-dimensional. They can move forward and backward, left and right, but the concept of up into the third dimension would be alien to them. If their universe was two-dimensional, then how might they become aware of a mysterious third dimension? Imagine that it rains one day. Tiny ripples in the third dimension move along the surface of the pond, and they are clearly visible to the fish. As these ripples move along the surface, the fish might conclude that there was a mysterious force that could illuminate their universe. Similarly, in this picture, we are the fish. We conduct our affairs in 3 spatial dimensions, unaware that there could be higher dimensions existing just beyond our senses. The only direct contact that we might have with the unseen fifth dimension is light, now viewed as ripples traveling along the fifth dimension. There was a reason why the Kaluza-Klein theory worked so well. Recall that unification through symmetry was one of Einstein's great strategies that led to relativity. In the Kaluza-Klein theory, electromagnetism and gravity were united because of a new symmetry, 5-dimensional general covariance. Although this picture was immediately appealing, unifying gravity and electromagnetism by introducing another dimension, there was still the nagging question, where was this fifth dimension? No experiment has ever, even to this day, picked up evidence of any higher dimension of space beyond length, width, and height. If these higher dimensions exist, then they must be extremely small, much smaller than an atom. For example, we know that if we release chlorine gas into a room, its atoms can slowly permeate all the nooks and crannies of any room without disappearing into some mysterious extra dimension. We know, therefore, that any hidden dimension must be smaller than any atom. In this new theory, if one makes the fifth dimension smaller than an atom, then it is consistent with all laboratory measurements, which have never detected the presence of the fifth dimension. Kaluza and Klein assumed that the fifth dimension was curled up into a small ball, too small to be experimentally observed. Wow, how sweet. How cute is this fifth dimension, though? They're curled up, just like Baji. Maybe there is a curled up fifth dimension, guys, like a little kitty cat. Sorry. I'm in awe. Although the Kaluza-Klein theory was a fresh, intriguing approach to unifying electromagnetism with gravity, Einstein eventually had doubts. The thought that the fifth dimension might not exist, that it might be a mathematical fiction or mirage, bothered him. So it bothered him because he's like, okay, when there are five dimensions, when Kaluza introduced a fifth dimension, then it works. But if you cannot find a physical evidence of the fifth dimension, then it remains a theory rather than something real. So also he had problems finding subatomic particles in the Kaluza-Klein theory. His goal was to derive the electron from his gravitational field equations, and try as he could not find any such solution. In hindsight, this was a tremendous missed opportunity for physics. If physicists had taken the Kaluza-Klein theory more seriously, they might have added more dimensions beyond five. As we increase the number of dimensions, Maxwell's field increases in number into what are called Young-Mills fields. Klein actually discovered the Young-Mills fields in the late 1930s, but his work was forgotten because of the chaos of World War II. Yep, they were having these wars too at that time, so it was not easy. It would take almost 2 decades before they were rediscovered in the mid-1950s. These Young-Mills fields now form the foundation of the current theory of the nuclear force. Almost all of subatomic physics is formulated in terms of them. After another 20 years, the Kaluza-Klein theory would be resurrected in the form of a new theory, string theory, now considered the leading candidate for a unified field theory. So, a lot of the people who work on string theory start with, first of all, general relativity as a theory for gravitation, because it is the more updated theory for gravitation, and because general relativity introduces the formalism that you need for all the math with the 4 dimensions. It's a more easy transition to including more dimensions, like we're talking about here with the 5th dimension being introduced by Kaluza and then kind of forgotten for a while, but actually that was sort of where things were headed. So a lot of people, like my professor who taught me general relativity, who taught the class that I took in GR, is a string theory guy, So like string theorists basically embrace this, notion or theory of having more dimensions, and it's their way of understanding the universe and so on and so forth. So basically, if you want to do string theory, for example, you have to start embracing these other types of pictures and doing the math in terms of what GR would introduce, and then taking it further. It's not just GR, but taking it further. Okay? So Einstein hedged his bets. If the Kaluza-Klein theory failed, then he would have to explore a different avenue toward the unified field theory. So I think he was basically, because they were not really finding any physical evidence for the 5th dimension, it's almost like if you say believe in the 5th dimension, or you believe in these other dimensions or more dimensions than just the 4 dimensions of space-time that we know and love, that we exist in, by saying that, okay, well, maybe there are these extra dimensions and the equations work out really nicely when you add extra dimensions, and you get more of this unification that he was seeking. But because we live in the 4 dimensions of space-time, and that's what we know and love, basically, even if these other dimensions were small, like he was saying about like the fish in the water under the lily pads who don't know about a dimension that exists, but they just don't experience it. Like maybe we experience space-time and that's it, and we just don't experience these other dimensions because they're small in our existence, right? Let's say that you do believe that, and there is good reason to believe that. Like, why not? That sounds like a pretty good theory, actually. But then, even then, physics being an experimental science, you still have to kind of prove that these other dimensions exist. String theory, I believe, is still considered a theory only. It's not considered like real, if you will, even though real physicists work on it, because of this lack of evidence about it. Basically, to make something real, to make something actual physical science, you have to experimentally prove it. But if the experiment is very difficult to design because you're trying to find something which is hard to find in our dimensions, then it's going to be very difficult. So I think that's kind of where we are. And even then, Einstein was basically saying, well, this sounds good. It sounds elegant that if we added another dimension that it kind of works out. But at the same time, it's like hedging your bets. It's like betting on something that may not pan out versus saying, okay, I'm going to abandon this and go in a different direction because I'm just not sure that this could ever be proved out. And even though, that's tempting to say that there is another dimension that we just don't know about because it's small, it can still feel a little bit like too convenient, like you're saying something, it's too placeholdery if you can't prove it out, if you can't show it with physical science. So that's kind of where he was, I think, with this. So he hedged his bets. But sometimes, just because something sounds crazy, to abandon it can also be a missed opportunity, like what the author here is saying, Michio Kaku, is because you actually could be advancing physics. You just don't know it yet. It's very difficult. That's where it becomes so difficult. That's where you have to kind of be okay with looking like a fool, honestly, because not everything starts as a concrete thing. Some things do start as a theory, and you have to have the faith to keep pursuing it and finding joy in life otherwise, even if that particular thing doesn't pan out, because that's kind of what it is. That's kind of what you're trying to do. You're trying to advance physics, which means that you're going somewhere that you don't know. And existing in places that you don't know is hard. Most people would not do it, but physicists may just have to in order to advance physics, okay? So Einstein hedged his bets. If the Kaluza-Klein theory failed, then he would have to explore a different avenue toward a unified field theory. His choice was to investigate geometries beyond Riemannian geometry. He consulted many mathematicians, and it became quickly obvious that this was a totally open field. In fact, at Einstein's urging, many mathematicians began to look into post-Riemannian geometries, or the theory of connections. To help him explore new possible universes. New geometries involving torsion and twisted spaces were soon developed as a consequence. These abstract spaces would have no application to physics for another 70 years until the arrival of superstring theory. Yay, superstring theory. So he basically, these new geometries that were being developed by mathematicians, this would all kind of contribute towards something even more complicated, superstring theory, which is something now. And it's laying the foundations for that. So he basically encouraged mathematicians to think beyond the Riemannian geometry in order to make this progress. So, sorry. So, this is interesting. We'll keep going. Working on post-Riemannian geometries was a nightmare. So, the challenge with asking people to work on post-Riemannian or beyond Riemannian geometries is, of course, that this is all very difficult. First of all, we don't really live in these multiple dimensions, in these like more than four dimensions, right? First of all, it's very difficult to imagine dimensions beyond space and time, like the space that we experience, which is 3D, and time, of course, makes it four-dimensional. So any imagination beyond that is a little bit difficult. On top of that, if you're kind of exploring geometries that are going even beyond the known structure, the known rules, if you will, it's very difficult. No, most people would probably not volunteer to get into these complications unless, of course, it was their passion. But that's what he was kind of seeking with all this. So working on post-Riemannian geometries was a nightmare. However, Einstein had no guiding physical principle to help him through the thicket of abstract equations. Previously, he used the equivalence principle and general covariance as compasses. Both were firmly rooted in experimental data. He had also relied on physical pictures to show him the way. With the unified field theory, however, he had no guiding physical principle or picture. So curious was the world about Einstein's work that a progress report he gave on the unified field theory to the Prussian Academy was reported to the New York Times, which even published parts of Einstein's papers. So soon there were hundreds of reporters swarming outside his home, hoping for a glimpse of him. So that was sort of the situation where people were just trying to get an update on what he thought of the unified field theory, just because he had come up with such big theories that were successful at that time, right? He came up with special theory of relativity and general theory of relativity. So whether there was anything there with the unified field theory, whether, E&M and gravitation could be unified somehow through another deeper, more insightful theory, was something that was still being looked at. That not only being looked at, but also people were curious about it. Like, people wanted Einstein to solve this and to get an update from him on this. So he might have even published about that, as we're seeing here. It was actually published in the New York Times, this progress report from him. Soon, there were hundreds of reporters swarming outside his home, hoping for a glimpse of him. Eddington wrote, "You may be amused to hear that one of our great department stores in London, Selfridges, has posted on its window your paper. The 6 pages pasted up side by side so that passers-by can read it all through. Large crowds gather around to read it." Einstein, however, would have traded all the adulation and praise in the world for a simple physical picture to guide his path. Gradually, other physicists began to hint that Einstein was on the wrong track and that his physical intuition was failing him. One critic was his friend and colleague, Wolfgang Pauli. So Wolfgang Pauli, famous for his Pauli exclusion principle, was his friend and colleague, thank God. One of the early pioneers of the quantum theory, so Pauli was, of course, working on the quantum theory. He's known for his Pauli exclusion principle, you can look that up, who was famous in scientific circles for his unsparing wit. He once said of a misguided physics paper, "It is not even wrong." To a colleague whose paper he had reviewed, he said, "I do not mind if you think slowly, but I do object when you publish more quickly than you think." After he heard a confused, incoherent seminar, he would say, "What you said was so confusing that one cannot tell whether it was nonsense or not." When fellow physicists complained that Pauli was too critical, he would reply, "Some people have very sensitive corns, and the only way to live with them is to step on these corns until they're used to it." His impression of the unified field theory was reflected by his famous comment that what God has torn asunder, let no man put together. Ironically, later Pauli would also catch the bug and propose his own version of the unified field theory. So he's basically saying that whatever Einstein was on, this direction was not going to pan out, according to Pauli. So sorry, hi, guest not found. How are you? How are you doing? So I actually realized that our main physics crowd kind of joins a little bit later at night. So I think I'm going to come back in a bit. I'll take a little bit of a break and come back and what do you call? Restart this chapter in a little bit, maybe like in an hour. Oh, good. Guess not found. So I think what we'll do is we'll just chill here for a little bit. I'll drink my tea and then I'll sign off. I'll let my phone charge because I think we'll finish the chapter tonight. We'll go pretty late into the night here. So I want my phone to be fully charged for this. So enjoy the kitty cats for a little while. We will start again in a little while. I'm going to drink my tea and hang out with you. And then I think I'll give it about an hour or so. I might start back up around 11 p.m. here in Boston time. So sort of that's kind of closer to when the physics people have been joining the live. So I think I got to wait for them for it to be the right time. Okay? Thank you for joining, though. Thank you for being here for now. Here's Baji and Suji. All right. Thank you for being here. We will be back shortly, okay? Thank you so much. Sorry about the interruptions. I'm gonna be back, I think, in an hour around 11:30 or so. That's when we had started the live, or maybe it was around 11:10 or so is when we'll come back, Eastern Standard Time, okay? So rejoin, I'll make a new live and rejoin it around 11:10 or so p.m. Eastern Standard Times. Thank you so much for being here. We'll be back.